The intention of this video is to construct the PERT project so that we can figure out, okay, how do I assign probabilities to a network so that when I'm bidding a project, I can give a reasonable time. So things that we've learned in class up to this point is, I have to have, in order to have a network, I have to have these activities and the predecessors. So there's my start, so that I can then start drawing the network. But in the PERT project, I don't know how long I'm going to be at each of these activities with any degree of certainty. So I choose to, whoops, that should be a B, and this one should be an M. Okay. So what we do is instead, since we don't have certainty, is we use the idea of our history of all the projects we've done that have involved node A. What was the most optimistic completion time? Well, there was one time where we finished it in 2 days, but usually it takes us 5, and then sometimes it takes us as many as 7. I mean, there are some more detailed guidelines, and I've given them in class, but that's kind of the gist of it. I have an optimistic time, a most likely time, a pessimistic time. And then from there, I can go ahead and construct this expected duration at each node and a variance at each node. But before I do that, I want to quickly construct the network that goes along just with columns B and C. So, the way to start that out, and I would say start it out because we've done this before. This network is constructed the exact same way every other network we've constructed so far was put together. And that is, I start with a single node. I first point to where that node comes from, so it's activity A. I then look up the amount of time that I'm going to be at activity A. Well, eventually it's going to be this expected time out here, but right now it's 0, it's empty. I have the early finish time, which is just the early start time plus the duration. I can calculate the late start time, which is the difference between the late finish time and the duration. And I can calculate the slack time, which is the amount of time or the time difference between the late finish and the early finish. Okay. Now, what we have not done yet is give an assignment to these 2 nodes that I'm highlighting right now. Because we got a lot of work to do before we can do any assignments for those nodes. So I've got to work from left to right through every node, assigning the early start time. So, I can think of that as I need to go through every node and calculate this early start time. Well, I've already done it in my picture. But let me at least outline what it is you're doing as you're moving from left to right. So what you're doing is I'm going to recover that so that you don't mix it with what we're doing. What we're doing is we're saying, okay, for me to move from node A to node B, A has to be finished. I know that from this arrangement up in the table. A precedes B. Okay? So the early start time there is equal to the early finish time in node A. Well, why is it just equal to one thing? Well, because there's only one edge connecting A to B. Similarly, I just move through. In order for me to work node C, I have to first complete node A. So the early start time at node C is equal to the early finish time at node A. Again, I'm just following the path back. I'm retrieving the early start time, the early finish time from that node behind it, and then moving to the next node. The only nodes that cause issues in this process are nodes like D that have 2 edges feeding into it. When 2 edges are feeding into it, I can't start D until both B and C are complete. So what I need is a number representing the time that it's going to take, so the maximum time to complete B and C. because I can't start D until I have finished B and C. That's why we end up with the maximum. And then I just move all the way through and I complete my construction. The next thing I do after I've completed all of these early start times is I go through and I construct all of the late finish times. First one's easy. It's just the first late finish is equal to the early finish here in node H, the last node. When I'm working backwards and calculating everything in these orange cells, all I've got to do is say, okay, the latest I can finish this is equal to the latest I can start this. There's only one edge going from right to left, so I just have this one thing to point to, R25 in my case. Okay, the only issues I ever have going from right to left is if I get to a node and there are two edges feeding back to the node B. So E and D both feed back to node B. And so I have to have B completed at the minimum start time, late start time for E and D, which is why I'm using that minimum function. Okay, so I don't want to go over this anymore. If you need to go over it more, go over the last video. I want to move on at this point. Okay, next thing we do, at every node, we're going to construct this expected time at each node. Now, I know I gave you a different function. You know, I said that we are going to use the ceiling, and then from that I'm going to say, okay, the ceiling of what? So I'm building the outside in. That's how you do math. Outside in. And then when you solve, you go inside out. Okay? So now I'm going to put in this expression that shows this expected value. So I want to go back and collect A plus M times 4 plus B. So in cell D3 for node A is the optimistic time. In cell E3, the node representing the most likely occurrence is given for node A. F3 for node A or activity A, that's the pessimistic time. I'm going to close that, so we'll add them all up first, and then I'm going to divide by 6. Okay? And that gives me my ceiling. Okay? Now, if you're not seeing that, pause the video, go back and watch it again. Do it over and over again until you've got it down. Okay? Now the variance. The variance, I don't want to do that ceiling function again. The variance is more sensitive than the mean is. So I want to keep some decimals. So all I'm going to do is I'm going to use this expression that gives me the variance at each node to do the calculation in the cell H3. So now notice how many parentheses I'm using, because I've got to get B minus A, then I've got to divide it by 6, and then I take that entire number, square it. Okay? So I've got B minus A. That operation occurs first. Then I divide by 6, and then I square it. So I'm working from the inside out. Okay? And that should give me the variance for that first node. Again, if you're not seeing it, pause the video, go back, look it over again and again until you've got it down. All right, so for every node, I need to construct or complete this calculation. If I can get the two calculations done correctly once, then I should be able to copy. So I'm going to copy, but what I want to copy are the formulas. That's why I'm making my choice under the paste special on the clipboard. It just has f of x on it. That's copying just the functions. Okay, so now what I have is an expression for every node, what the expected duration of time is at every node, and the variance at that node. All right. Now notice that if I have this set up right, which I'm pretty comfortable with, that my network fills in automatically. As soon as I have this expected time, you know, in every node, this number that I'm highlighting fills in just as soon as I have this expected time calculation. Okay? Now what I have to do is find the critical path. Well, the critical path is, okay, I need to look at the slack time in each node, and I'm looking for a path through this decision tree where along the path every node slack time is 0. One way I have found this is to use this function, this if-then function. Is it a big deal? No, you could get through this class without an if-then function. I really, though, would like you to use it because when you leave this class, this little function is going to be extremely useful unless you like to do things over and over and over again. I mean, if you enjoy monotonous repetition, forget the if-then statement. Okay? But if you like things that handle themselves and complete quickly, learn how to use it. What it says is if B22, so now it's down here at activity A, looking at the slack time, it says if it's not 0, so that's just a less than greater sign, less than and greater than sign back to back. So if this is not 0, I want you to leave the cell empty. Otherwise, put the letter A there. Okay. Well, I want to copy this down this entire column so that I can see the critical path. And then once I have the critical path, I'm kind of done with the network. Now at this point, I'm now on to looking at the network as a whole and not the pieces of the network one at a time. Okay? So the network as a whole also needs to have a variance, and I've written it here as the variance for the network as a whole. Well, I need to sum, that's what this gigantic capital sigma means, if you recall from math. I'm going to sum only the variance nodes on the critical path. Okay? Well, A is on the critical path, so I want the variance from A. All right, well, B is not on the critical path. See, I'm using that if-then function. So I'm just going to paste special. And notice everything on the critical path, the network variance is showing up. Well, I'm sorry, the variance at each node on the critical path is showing up. For the network as a whole, what I need to do is I need to add up those variances. So I'm just going to take the sum of the variances on the critical path. All right, well, the next thing we're asked to do is find the mean for the entire network. Well, according to this, what I'm going to do is I'm going to look at the early finish time across all nodes and find the maximum value. I even know where to look for that, right? Because I know as I move from left to right that the early finish times are going to continue to get larger and larger. So I know that in the last node is where I'm going to find that average that I'm looking for. Well, how does this translate into probabilities? Okay. Well, here's what I've tried to do. Don't pay any attention to the calculations. I just wanted the picture. We are actually making a statement that this distribution, the distribution across this network is normally distributed. And the peak, the most likely outcome, or the probability of 50, happens right at the mean. So it's right there at the peak. Half the time will be below that in terms of total live time. Half the time will be above that in terms of total time. Okay? So I want to use this idea to help me calculate probabilities, this distribution idea. Okay? So we can calculate probabilities in a couple of ways. One of them, we could look at the scale. Time is measured on this axis. May as well put it in there. And probabilities are measured on the vertical axis. Now, of course, I can't, in a continuous setting like this is the word math word being used is continuous, I can't take a probability at a point. It doesn't have any meaning. So what I can do is I can take probabilities of regions, which is what this is trying to say. What if I looked at the probability that my time comes out less than some t0? So here I'm letting t0 be these various numbers, and I'm saying, okay, well, what's the probability that we'll complete before these times? Well, I used the following function. Norm distribution, I looked at the time, and then I got the mean. That square root gets me the standard deviation, and true tells me to add up all the area all the way to the left in this picture up until the time period t in this table. So I push that button and it says, oh, 50% of the time, or the probability that I'm finished within 39 days is 50%. Well, we knew that. We knew that because 39 was our mean. And we knew from a symmetric distribution that half the time we're going to finish before the mean, half the time we're going to finish above the mean. All right, well, let's just copy and kind of get a feel. Okay. So 40 days, 61% chance. 44 days, 92% chance. I'm going to be done within 49 days. I've got a 99.75% chance that I will have this finished in 49 days. Okay. Now, frequently the question comes kind of on the flip side. What I mean by that is oftentimes we're given the probability, this column, and we're asked to find the time. So instead of going from left to right, we're going from right to left. Okay? So in a math setting, I think of going from left to right as moving forward, meaning, I'm choosing something on the horizontal axis and then calculating an area underneath this curve. Whereas this other problem is what I like to call an inverse problem. This time I have an area and I'm asked to find the number on the axis that corresponds to the area. That is frequently how our questions are asked. So I have to use a different function. I use this norm inverse. The first argument in the function is this probability. The second argument in the function is the mean of the distribution. And the third argument in the function is the standard deviation, or the square root of the variance of the entire network. And if I could get that in once correctly, I could answer questions about any probability, any one you want, right? So, what is a 25% sure will be done? Well, I'm 25% sure we'll be done in 36 and 6/10 of a day. Okay, my hope. My hope is that you will use this video to kind of go back and forth and back. Hopefully I've explained enough detail that you can stop or pause and go back and pick things up. And then we can kind of I want you to be able to get this. I know all of you can get this. What I need you to do is put your best effort into it. And if you're not able to get it from what I'm doing here, then just come and ask me some questions. And then we can try to clear this up. Because this is just one thing that we're doing, but it's a fairly important calculation. We will see networks again. Not only once, but we will see them again. So anyway, hope this helps. Let me know if you need more help.